So yeah, uh, thank you for the feedback from one of the student. So I missed the calculation at here. The average of user one. Okay, the average of user one. Uh, Actually, there are some issues with this one. If you look at the numbers, 3 plus 1 plus 2 plus 3 divided by 4, it means 9 divided by 4. 9 divided by 4 means 2.25, but it is 2.4. Okay, so I just realized that this original version, they use all the values. Okay. So the book may use all the values. It means it will be 3 plus 1 plus 2 plus 3 plus 3 divided by 5. So it means 9 plus 3, it is 12 divided by 5. Okay. If it is 12 divided by 5, then it is exactly 2.4. Okay. So it is exactly with this one. If you calculate this one as well, it is based on the 5 values. So the authors mentioned that if we include this one, actually it is a kind of bias because we are going to use this value for the prediction. Meanwhile, we also include this number with the subtraction of the average. But because this book, this is the original version, okay, so let's just use the original version with finding the average for all of the ratings. Okay. So some modified version, they will use only until the items which is not about the prediction. This is more neutral. Okay. But this early or this original version, they include every of this rating. So when I give the problems in the exam, I think you can consider the average for all items like this one. Okay. So there are some ways to improve the metrics. How? As we already know uh, from this utility metrics, agreement on commonly liked item is not so informative as agreement on controversial items. What does it mean? Maybe I like one movie and one of you like the movie that I like, but it can be coincidence. But usually, the controversial items is more informative. The controversial means something that you don't like or something it is in the social media. It appears that this movie is bad, this movie is not good, and then yeah, there are many controversial. So many people will have the same agreement on that one. It means if you give like one, other people may give also one, it is more informative rather than if you give 5 and your friend give 5, it might be not that informative. For example, in this case, like the Toy Story and Spider-Man are different rated movies. Okay, maybe this is the Toy Story, and then this is the Spider-Man. We can see 5 and 4, 3 and 2, 4 and 4, 3 and 1, 1 and 5. Okay. So it is controversial. So the other possible solution when the nearest neighbor ratings may not be valuable if you can give more weight to items that have higher variance. What does it mean? Higher variance. So if all users give this movie 5, 5, 5, 5, 5, so it is low variance. Okay. So we need to understand low variance. So if it is low variance, then user give almost the same rating. 5, 4, 5, 4, 5, 4. So it is low variance. But if it is high variance, some users give 5, some users give 1, some users give 2, some users give 4, and we don't know. So those kind of items we can give weight or 가중치. The other things that we can improve the matrix or the prediction is about the value of number of correlated items. Use significance weighting. For example, linearly reducing the weight when the number of correlated items is low. You already have this table. It assumes that every users have the rating. But in the real world, this will be the case. Some users may not give rating. It will be missing. So if it is missing, then we call it this is co-rated item. Alice, user 1, user 2, they have co-rated item. But those 3 users, they are not co-rated item because they don't give any rating to this item. So we need to understand the value of number of correlated items. So if it is low variance, no problem. If it has high variance, we need to check. So there's another method. We can use the significant weighting. For example, linearly reducing the weight when the number of correlated items is low. So if this one, all the items we have the correlated, but we have only 3. We have only 3. This one we have 4. So the low correlated items means the number of items that have co-users or users who give the rating on that item. If it is low, we can reduce. So we can just remove the item. In this case, if you want to remove the Toy Story and Zootopia, yeah, it is possible because they are low compared to the Mission Impossible and the Spider-Man. Case amplification. Give more weight to the very similar neighbors or where the similarity value is close to 1. I know that Alice and user 1, the similarity value is 0.85. So it is very similar. Then I can give more weight to Alice and user compared to Alice and user 2. The other possible way to improve the metric is neighborhood selection. So as I mentioned to you, we can use the similarity principle. For example, I want to have the similarity value which is higher and equal to 0.5. Then I can select the users where the similarity value is higher or equal to 0.5. Maybe there will be n users, so we will select those n users. Or we can use fixed number of neighbors. In the MovieLens dataset, some papers they mention 20. So if we can find 20 users, let's use that 20 users for the prediction. If the movie is a hit movie, it's like the box office movie, then you can select 100 similar users. Okay. So that's the way to find the fixed number of neighbors. So what we already did on the previous one is the user-based collaborative filtering. The meaning by user-based is I use the information from the user and I calculate the similarity between the users. Now, there is another collaborative filtering. It is called item-based collaborative filtering. If it is item-based collaborative filtering, it means I want to use the similarity between items, not the users, to make predictions. So I want to know item 2, item 3, item 4, item 5, and then let's say I want to predict the rating of Alice in the item 5. So I need to know what are the items that are similar to item 5. So let's say maybe this is coffee. So I can try to find the items that have the similar ratings to coffee. So that will be another approach. So we can take Alice rating for this item to predict the rating for item 5. So let's say if I want to check this item 5, maybe the similar to this item is item 4 and item 1. And I will use this number and this number to predict this number. That's the meaning by item-based collaborative filtering. Now let's use the cosine similarity. Okay. So we already have an example of the cosine similarity like this one. In some research, they mentioned that it produces better results in item-to-item filtering. And ratings are seen as factor in n-dimensional space. N-dimensional space, yeah, it means if I have the rating of Alice, we can have the factor. So like this one, we call this is one factor. Because this is one factor. N means the number of items. If the perspective is about the item, then we can look at this is as one factor. So this is the factor index 0, 1, 2, 3. So the similarity is calculated based on the angle between the factor, or the range is between 0 and 1. So if we have this cosine similarity, then we can calculate. Let's say I want to calculate the similarity between the item A and B. So I want to know the angle between those two items. So you already have the example using this formula. Okay. So this is one of the example. And there is another way to calculate the cosine similarity. We call it adjusted cosine similarity. That's what adjusted. It means we want to take the average. Okay. We want to take the average of user ratings into account and transform the original rating. When we use the cosine similarity, the cosine similarity has range between 0 and 1. When we use the adjusted cosine similarity, the range will be from -1 to 1. So later we will use this kind of equation. So the idea is the same with the person correlation that we already did before. We will minus with the average. We will minus with the average. So let's look at this one. I want to know the similarity between item 1 and item 5. So I have the item 1, item 5. Then I can just multiply 3 multiplied by 3. Okay, 5 multiplied by 4, 4 multiplied by 3, and then 1 multiplied by 1. And then divided by the square root of 3, 5, 4, and 1. All will be powered by 2. And then 3, 4, 3, and 1. All will be powered by 2. And I can get a value 0.99. It means item 1 and item 5 has high similarity for the rating given by the user 1, 2, 3, and 4. Okay. Now, what is adjusted cosine similarity? Adjusted. We want to modify Young cosine similarity. Okay. It means we want to convert conversion from original value to mean adjusted ratings database. Okay, let's see. I have this rating So Alice gave item 1 5, and then she gave item 2 rating 3, she gave item 3 4, she gave item 4 and 4. Now what is the average of the rating? We have 5 plus 3 plus 4 plus 4, which is 4 is the average. In order to get the mean adjusted rating database, I will minus for every value here with the average. 5 minus 4, it will be 1. 3 minus 4, it will be minus 1. 4 minus 4, it will be 0. 4 minus 4, it will be 0. Okay. So we call this is the mean adjusted rating field. Now let's see with this user form. Okay, let's look at the average. Is 1 plus 5 plus 5 plus 2 plus 1 divided by 5. I guess this is the case. 10 plus 4, 14 divided by 5. Here it is 2.8. Okay. Then I can adjust each of value. 1 minus 2.8, it will be minus 1.8. And 5 minus 2.8, it will be 2.8. So the other value also, see, you can calculate the average. We can calculate the average. We can calculate the average, and you will get a new matrix like this. Because this is a mean adjusted rating table. Okay. After I have this mean adjusted ratings database, we can apply the cosine similarity. What is the cosine similarity? So cosine similarity means we want to get the value for every of the cell. Let's say I want to know the similarity between item 5 and item 1. I can do again the calculation. I want to calculate the item 1 and item 5. So 0.6 and 0.6. Okay. So this is 0.6 multiplied by 0.6, and then 0.2 multiplied by 1.2, and then minus 0.2 multiplied by 0.8, and then minus 1.8 multiplied by minus 1.8, divided by every of the value in the item 1, and then every of the value in the item 5. And don't forget to do the square root, So we can get the value of the similarity is 0.8. What was the value before? This is the value 0.8 from the mean adjusted rating database. This is the value from the cosine similarity with the original rating. Okay. After we have the similarity value, now we want to do the prediction. What is the prediction? This is the common prediction function, or maybe this is the original prediction function. We use the similarity of the particular items, the rated items in the user U for the particular product multiplied by the RUI. So I put this one is U is the user, P is the product that we want to predict, and the I is the rating of either items. Neighborhood size is typically also limited to a specific size. What does it mean by neighborhood size? So here I have item A, and then how many users do I have? In this case, 4. But if there are so many users, do we need to include all of them? It's difficult. Usually, we will determine the neighborhood size. Some of them may be blank, 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 blank. And if it is blank, we cannot include. Not all neighbors are taken into account for the prediction. So it means if you have many users, but we cannot include all the users. An analysis of the movie lens data set. So yeah, maybe next week we will learn about the movie lens data set. So in the movie lens data set, it indicates that in most real world situation, a neighborhood 20 to 50 neighbors seems reasonable. So these neighborhoods, if it is about the users, then yeah, 20 or 50 users. It can be also the same with the item. If it is about the item, maybe about 20 until 50 items are still reasonable. Now, by looking at the previous result, okay, I already gave the similarity measures. The item 1 and item 5, the value of the similarity is 0.8. Item 2 and item 5, the similarity is minus 0.9. Item 3 and item 5 minus 0.76. And item 4 and item 5 is 0.4. So based on this one, which items are similar to item 5? We can just say that, okay, I will take the positive one. Okay, I exclude the negative. If I include only the positive, so the most similar items are item 1 and item 4, which is 0.8 and 0.42. So I want to know, Alice rate 5 to item 1 and Alice rate 4 to item 4. So what is the prediction for the item 5 of Alice? So we can use in this one is from this formula. The similarity of the items. So the similarity of item 1 and item 5 is 0.8. The similarity of item 1 and item 4 and item 5 is 0.4. Okay, so the 0.8, it is from the similarity value, and this 0.4 is from this one. And I know that Alice give 5 to item 1, so I will multiply 0.8 with 5, plus I have the value, similarity value of item 4, which is 0.42, and Alice give rating 4 to the item 4. So after I have this calculation, I divide with this value, so this is the rating prediction. 4.65 based on the ratings given by Alice Roberts. Question. So what is the difference between cosine similarity and adjusted cosine similarity? The output range. Okay. The output range for cosine, it will be from 0 until 1. What about the adjusted? -1 to 1. From -1 to 1. Okay, that's good. So when we use the adjusted cosine similarity, it is possible to have negative. So what is the effect of by using adjusted cosine similarity? Compared to the cosine similarity, what is the effect by using the adjusted cosine similarity? More approximate. More approximate also. What do you mean by approximate? If we look at the result, the similarity of item 5 and item 1 with the adjusted cosine similarity is 0.8. With the cosine similarity, the similarity is 0.99. Is it approximate? Scalability. The normal scalability. Okay, that's good. Because in the item, when we are considering the item, we do not know who's give the rating, which user give the rating. So we want to know the normality or the distribution. So using the adjusted cosine similarity, we are trying to find more on the distribution. This example is showing the distribution of the items, but actually we can also do the distribution of the users. In some research, they mentioned that when we are doing the item-based filtering, okay, when we use the item-based filtering, there should be some pre-processing. So what we already have, the value in our example, we already have the good rating. But if we don't have a good rating table, we need to do some pre-processing. Item-based filtering does not solve the scalability problem itself. So what does it mean by this scalability? Okay. The pre-processing approach by Amazon.com in 2003. Okay. So they try to calculate all pairwise item similarity in advance. The neighborhood to be used at runtime is typically rather small because only items are taken into account which the user has rated. So what does it mean by this one? When you are doing the online shop like Amazon or Coupang, so there are maybe millions of items. So in order to calculate the item similarities, it will be very, very long time. So that's why they calculate all pairwise item similarity in advance. In advance means they calculate first. Okay. Because if they calculate before the prediction, it will be time consuming. So they already have the database of the similarity before they do the prediction. And the neighborhood to be used at the runtime is typically rather small. You know, the neighborhood. The neighborhood means, in this case, we are using item 1 and item 4. So when we choose this neighborhood, we need to choose it small. Because if you choose many neighborhoods, it will be more complicated to understand. So Amazon also gave that idea. So because only items are taken into account which the user has rated. So not all users give the rating. And this is the idea. Item similarities are supposed to be more stable than user similarities. So if the items has rating, there is a potential that other users also give rating to that item. So item similarities are more stable. The memory. Okay. So the scalability actually it is about the memory requirement. If you already joined the data structure class, okay, you know about the big O. So in the big O notation means if you have a lot of memories to compute, it will be difficult to recommend. So in theory, if you use the pairwise similarities, so if you use the pairwise similarities, like this one, so if it is a matrix, let's say this is n multiplied by m. We have n users and we have m items. So the computation will be at big O n multiplied by m. And let's suppose we have the pair, which is the items. Let's say the number of items and the number of users are the same. Then we will have the big O of n power of 2. So it is quadratic. In theory, yeah, it is like n power of 2, but in practice, this is significantly lower. Items with no co-ratings, because some items may have null. If there are some nulls, then we can remove it. For example, like this example. If this example, then yeah, we do not need to calculate. So in theory, we will calculate all n power of 2. But in the reality, if there are some missing value like this one, we can remove from the calculation. Further reduction possible, yeah, we can set the minimum threshold for the co-rating. Like I mentioned before, if there are 5 users who gave the rating, then okay, we can include them. But if there are only 3 users give rating, we can exclude those items. Or limit the neighborhood size. If we limit the neighborhood size, for example, we just consider only 20 users, or if we consider only 20 items, maybe it will affect the recommendation accuracy. Yeah, anyway, there are so many aspects for the consideration in the recommendation. You already know many things about the ratings. Last time, in the first part of our lecture, we learned about the explicit rating. The explicit rating is explicit. You can see, you can look, you can understand the ratings. Is probably the most precise rating. And it is most commonly used. You know the ratings that we learn is 1 until 5. There's another rating 1 until 7. And there are many research topics on this one. So yeah, if you do the assignment, you can look also some papers that deals with different kind of, we call it granularity. Okay. What is granularity? So we can have from 1 until 5. So the granularity is small. We can have 1 until 7. So the granularity is become wider. We can have 1 until 10. So it is wider. We can have 1 until 100. Okay. So the granularity becomes wider and wider. So some domain indication that 10-point scale is better accepted in movie domain. So 10, it means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. An even more fine grain scale, fine grain. Do you know this word? You know, rock. Rock is big. So we can say this is coarse grain. Rock. Sometimes we call this is coarse grain. It is quite big. It is still, yeah, we call it coarse. But if it is like sand, we call it this is fine grain because very small. Okay. So the same with this kind of numbers. If we use the integer value, then the value is coarse. But some of this recommended, have you ever heard? I don't know. I think it is more common in Korea. Stand up comedian. So there's a research by this guy, Goldberg, in 2001. So the scale is from -10 to 10. And it uses continuous scale. Like this one. -7.82. So this is very fine. Because it is not integer value. It is a real value. And they use also the graphical input, like this one. So if it is -1, this is 1. So we can see the graphical input, whether it is, for example, smooth or rough, bumpy or flat, hard or soft. So we can use this one as well as a kind of rating, or this is explicit. And yeah, sometimes we cannot immediately. How you can determine it is 0.22? It is difficult to say, but there are some research and there are some tools they use this kind of rating. People said that this is no precision loss from the discretization. It means if we use the number 1, 2, 3, 4, 5, actually we ask the users to choose. Okay, choose only from 5. It's easy. But the user may want 2.5, something in between. We do not know. But if we give this one, like this value, so they mentioned that no precision loss. It's more exact. And user preferences can be captured at the finer granularity. With very small value, we can get the insight from the user precisely. And users actually like the graphical interaction method. So if you give the user with this graphical, the user tend to choose, or the user tend to give the rating. But of course, it is difficult to ask the user to give this rating because it is too complex. The usual user, they like to give rating only like this. It's easy. That's the issue. And there can be the multi-dimensional ratings. What is it? We can ask the user, okay, what about the actors? Please give the ratings about the actors. And then you can ask another rating. Can you give the rating about the sound? Or there can be another kind of rating. Can you give the rating about the music? Can you give the rating about the story of the movie? So we have multi-dimension. So this is also more complicated. So if it is about the explicit rating, so it is about the ratings or review. So sometimes we can get this review with text. The movie is good, but it is too long. So it is review in the text. Maybe with this kind of review, we can know that, okay, the rating is 5, but there's still some weakness of the movie. We can try to capture this one with some other techniques. Auctions. So auctions, it means when we want to buy some products, we do bidding. Maybe, okay, do you want to buy this smartphone? Okay, what price do you want? Okay, one student said back Manon. Okay. Another student said, back Oman. Another student said, back, okay, I want back Sigmanon. So every value we capture. So we can say this is also an explicit rating. Yeah, the main problems, users not always willing to rate many items. They just want to put one rating, finish. And the number of available ratings could be too small. We call this is sparse rating matrix. So if we have this kind of matrix, it is sparse. We need to fill with zero. So it is more complicated to do the prediction. The quality of the prediction will be poor. So how to stimulate users to rate more items? Okay, we will discuss about this one. So before doing this one, let's have a break.